Okay guys, so finally we'll give the proof of the Lagrange multiplier theorem. Let's recall the details. We have a function f from some open set u in D space into the reals. We're assuming it's a C1 function. That's what we call the objective function. And that's the thing to be maximized or minimized. Okay, we also have the constraint function, which is possibly vector valued. Let's assume that that's defined in some open region of D space, capital V. But it's, say, has k dimensional outputs, and also that it's a C1 function, which really means that if I write the outputs in terms of component functions, there are k of them, and each gk, is a C1 function on that same domain, capital V. Right? Now, the number of constraints, so the reason it's k is because we're going to have k constraints. K, like, separate scalar constraints, which are of the form g sub, well, not k necessarily, but g sub j of x equals some constant c sub j. And j is going to run from 1 to k. So we'll have basically k constraint equations, but we put them together in the form of a single vector equation. But how many constraints are we allowed to have? So we're going to assume that we have at least one constraint, otherwise the theorem would not be necessary if we had 0 constraints. It would just be a standard optimization problem. We know how to do optimization with no constraints, so like k equals 0 is irrelevant. But we do want to limit k to be at most d, because if we have too many constraints, then it's going to be very difficult, if not impossible, to get all those constraints satisfied simultaneously. So like the set of points that satisfy all those constraints simultaneously will be empty. And the problem with that is that if you restrict the function f to the empty set, you get the empty function. It has an empty domain. And you really can't do calculus on the empty function. So to avoid that, we're going to make sure that we don't have too many constraints. We limit the number of constraints, which is k, to be at most d. Okay? And we're also going to assume that the two domains, u and v, have a non-empty intersection, which we're going to call w. And notice that w is also open. Reason is because u and v are both open, by assumption. Remember that. That's what this little circle here means. It's an open subset of D space. And then v is also an open subset. Now, in general, intersections of open sets are not necessarily open if you have an infinite number of them. But if you have only a finite number of them, such as 2, the intersection is also an open set, as we proved a long time ago. Okay, so that w is certainly an open set, but the point is that we assume it's not empty. That's the main thing that I'm actually assuming here. That w is not the empty set. And it's clear why. F and g have to be related to each other. So if their domains didn't overlap, then we really couldn't do anything with both of them simultaneously. So their domains have to overlap. Okay, now we're going to also choose a value of c, which is the vector, like a constant vector in k space, that has these things as its components. These constants will be put together into a single vector. Okay, but we're going to be considering this equation, g of x equals c, which is really just a shorthand for g1 of x equals c1 and g2 of x equals c2, and so on. But we want to make sure that this solution, or sorry, that this equation rather has some solutions. We want to make sure it has some solutions. In other words, the solution set is not empty. For that to happen, c has to be in the range of g. So c is like a value of g. It's taken on at least one point x. But moreover, more specifically, the point x that satisfies this equation should also be in w, because we want that point to be in both domains simultaneously, both in u and in v. So here's what I'm going to do. Let me just erase all this stuff so that I have room to write it. Okay, the vector c, we're going to assume, is in the image of the set w under the mapping g. So what that means is that there exists a particular point x0 that's in w, so in other words, it's in both of the domains, and satisfies the equation g of x0 equals c. So the value c is actually taken on by the function g, precisely at this point x0, and that point x0 happens to belong to w. In other words, it belongs to both domains. So we're assuming the existence of such a point. And that means that c is in the image of w, because c is the value of g at some point in w. C is precisely the value that g takes on at some point that happens to lie in w. So that's what this exactly means. It's the image of the set w under the mapping g. So the point x0, which is in this set, when you plug it into g, belongs to this image. And that's what c is. C is exactly the value of g of x0. Okay. So anyway, that's a key assumption, just to make sure that the constraint equation has some solutions. the set of solutions of the constraint equation is not the empty set. Okay, good. Then we have the constraint set itself. So let me just title it that way. Our constraint set we call S, and it consists of all points in W. In fact, let me write it a slightly different way. I'll write it as like the set of all points X in D space that satisfy two conditions. Condition 1 is that they have to belong to W. The reason for that condition is so that X can be plugged into both functions F and G. The point X has to be in the domains of both of those functions if we want to plug it into both of those functions, which we do. And at the same time, it has to satisfy the constraint equation, G of X equals C. So that's the constraint set. And notice that it's not the empty set. It's not the empty set because the point X naught is in it, at least. And of course there may be many other points in it. Usually there's an infinite number of points, uncountably many points, uncountably infinitely many points in the constraint set. But we know that there's at least one, by assumption. Because notice that X naught satisfies those two conditions. X naught does belong to W, and it does satisfy the constraint equation. So both of the conditions belonging to W and satisfying the constraint equation, they're both satisfied by X naught. So X naught certainly belongs to that set S. Okay, so that's the set that we're going to restrict the function to. We're going to consider, in other words, the restriction of f, the objective function, to that constraint set, which is a function that has S as its domain, and it goes into the reals. Right, so the domain is now restricted to just be that set S. And notice that makes sense because S is a subset of W. Why is that? Well, it's because the set S consists of all points X that already belong to W and satisfy some additional constraint. So every element of S is already in W, just by definition. That means S is entirely contained within W. Okay, and W is contained fully within U, because W is the intersection. In fact, let me just write that explicitly. The intersection of U and V is contained within U. Okay, and U, of course, is the domain of the function f. So, in other words, S is within the domain of the original function, and therefore it makes sense to restrict the function f to that subset of the domain. Okay, now we also need to assume the existence of the relevant max or min. So there are really two versions of this theorem. There's a version for maxes and there's a version for mins. They're pretty much exactly identical. I'm going to state only the version for maxes, and the version for mins is going to be virtually identical, and I'll just leave it unstated. So one more assumption is that we're going to assume the existence of a point P in the set S, such that for all other points X in that same set S, the value of f, and I really can restrict it to S because those are the only relevant points, the value of that function at X is less than or equal to its value at P. Okay. Now I should point out that this equation that I just wrote down, let me put it in a box, I wrote it using the restriction notation, f restricted to S, because that's really the function we need to keep in mind. That's the function we want to study, and its domain is S. Okay. But we can also write that same equation if we choose this way, just for all X in S. Because you see that when you have a function f and you take a restriction of it to some subset of its domain, these two functions agree with each other in value at all points X in the common domain. Okay, now where do they disagree? Well, let's say I have a point Y that's not in that common domain. Like it's in the domain of the original function, but it's not in S. It's not in that subset. Rather, it's in the difference. Take the domain of the original function and just delete the set S. Suppose I have a point Y that's like that. Well, then these don't agree simply because this is undefined. Right? The reason it's undefined is because Y is not in the domain of this function, which is S. And so the value of that function at Y makes no sense. Okay, so, but, as long as we're restricted to points that are in that set, you can always rewrite this expression in this way. And that's what I've done with this equation here. You can always just write it this way if you like. And it's usually simpler to write it that way. Okay, so let me leave that just like that. Okay, so notice we're assuming the existence. We have to assume the existence of the relevant global maximum. That's what this point P is. P is a global maximum point, which is not necessarily unique for the function f restricted to S. When I say that's not necessarily unique, what I mean is that there may be several points where the global maximum is taken on, but we're just assuming the existence of at least one such point. Okay, so the global max value the global maximum value, which is the value of this function at P. We can call it like max of f on S, may be taken on by the function at other points besides P. Other points in S, I really should say. So just keep that in mind. P is just one point where that global max value is taken on. And it might be unique, but it doesn't have to be. However, we do need to assume the existence of the global max. The existence of it does not follow from this theorem. Rather, this theorem uses the existence as a hypothesis. So in practice, when you're doing actual examples, you have to establish the existence of the global max, if you think there is one. You have to prove it using some other theorem like the extreme value theorem or the max value theorem. Okay. Anyway, the conclusion is that the point P satisfies one of two conditions. And let's call them the Lagrange system, which I'll call LS for short, or the degeneracy system, which I'll call DS for short. And now I'm going to just elucidate or remind you of what those conditions are. Okay, the Lagrange system consists of two conditions. There's the Lagrange equation, which says that the gradient of f at x is a linear combination with some coefficients lambda j of the gradients of the component functions g sub j at x. J runs from 1 to k because they're k component functions, g1, g2 through gk. Right, so that's the Lagrange equation. And then there's the constraint equation, which is g of x equals c. Okay, those two together is what we call the Lagrange system. Like the conjunction of the two is what I'm going to call the Lagrange system. So notice that this is really k or d plus k equations in d plus k variables. The variables being the components of x. There are d of those because x is a d-dimensional vector. And then there's the lambda 1, like the lambdas, right? Lambda 1, lambda 2 through lambda k, which let's just put into a vector and call that vector lambda. That's a vector in k space. So we have k plus d or d plus k variables. Why do we have d plus k equations? Okay, well, it's pretty easy to see that. This really breaks down into k equations. g1 equals c1, and then gk of x equals ck. So there are really k equations here. And then this one here breaks down into d equations, because the gradient really is like df dx1. And then you have this sum, and the first component of those other gradients are going to be like dgj dx1. So that's going to be the first of those Lagrange equations. But there are d of those. So you have a total of d equations there. Okay, why are there d of these? Well, there are d of those x variables, right? So this is only with respect to x1. Then you'll have a second equation where you're differentiating with respect to x2, and then x3, and so on, up to x sub d. So you see that you have together d plus k equations. And these are not linear equations, although they are linear in the lambdas. That's kind of interesting to notice. These equations are linear in the variables lambda 1 through lambda k. What I mean by that is that lambda 1 through lambda k appear in these equations in a very simple way, only multiplied by some expressions that don't have lambdas, and then added together. But the dependency on the x variables is nonlinear in general. So this is not a very simple system of equations to solve. In fact, it's usually impossible to solve it analytically, to solve it exactly. Usually we have to just numerically approximate the solutions somehow. Sometimes we can use graphing technology to visually see where the solutions are and then zoom in on them and approximate them. Okay, but you need usually some numerical or computational techniques to get approximations to the actual solutions. But in certain simple cases we can solve algebraically. And those are the cases where the standard examples tend to focus on. Okay, anyway, so that's the Lagrange system. Now, when we say that the point P satisfies that, that's a little bit of a misnomer. You have to understand it. You have to understand it properly. The expression that P satisfies the Lagrange system is really shorthand. It's a shorthand conventional expression to mean that there exists a lambda of P in K space, such that P and lambda of P together, jointly, satisfy that Lagrange system. See, the lambda depends on P. That's why I'm writing it as lambda of P. It's like a function of P. Sorry, I ran out of room there. So if you have two p values, you have to remember, like back here, we said that this global max value may be taken on at many different points besides p. Like it may be also taken on at some other point, q, for instance. Well, then p is going to have its own lambda, which we can call lambda of p, but q is going to have its own lambda value, which we can call lambda of q, if it also satisfies the Lagrange system. You have to understand, though, that p and q, like if you have 2 points where the global max is taken at both of them, let's say I have p and q, both in the set S, and the function f restricted to S takes on its global max value at both of those points. They don't both have to satisfy the Lagrange system, because one of them might satisfy the Lagrange system and the other might satisfy the degeneracy system. Or they might both satisfy the degeneracy system. But they could both satisfy the Lagrange system. Any combination is possible. So what I'm saying here is that if Q does satisfy the Lagrange system, then it's going to do so when paired with its own lambda. In other words, Q gets paired with some lambda vector, and P gets paired with some other lambda vector. But those two lambda vectors don't have to be the same. The lambda that gets paired with P is lambda of P. The lambda that gets paired with Q is lambda of Q, and they don't have to be the same. So that's why I'm writing it that way. It sort of depends on P. Okay, but the existence of such a lambda vector in K-space, such that when you pair the two of them together, they jointly satisfy the Lagrange system. That's really what we mean when we say, kind of sloppily, that P by itself satisfies the Lagrange system. It means that P satisfies it together with some suitable lambda that exists. Because remember that the Lagrange system is not a system in d variables. P only has d coordinates. The point P only has d coordinates, because it's a point in d-dimensional space. So we can write it as, let's say P1, P2, through P sub d. That's not enough coordinates to satisfy an equation that has d plus k variables. So when we say that it satisfies the Lagrange system, it's really just a conventional shorthand. That's short for this whole statement here, that there exists a corresponding lambda vector, corresponding to P, such that the two of them together give you d plus k values that satisfy the Lagrange system. Okay, so I'll use the short phrasing from now on, as long as it's understood what we mean. All right, so that's one alternative. Alternative one is that the point P satisfies the Lagrange system in this sense. The other alternative is that it satisfies the degeneracy system. And that also has two conditions. There's the degeneracy equation itself, and I'm going to write that this way. You take g prime of x, which is the Jacobean derivative matrix, multiply it by its own transpose, and then take the determinant, and set that equal to 0. Okay, now why we do all those steps is going to become clear as we work. But for now, just notice that this is only one scalar equation. It's one scalar valued equation in d variables. The d variables are just the coordinates of x, since that's the only vector that appears. And the reason it's one scalar valued equation is because the determinant is a scalar valued function. The determinant is just a numerical valued function. Okay. So that's the degeneracy equation, and then of course we need to put that together with the constraint equation, which is again g of x equals c. Okay. Now in this case we also need one more condition, which I'm just going to call the location condition, and that just says that x belongs to the set W. Those are the only points we care about, the points that are in both of those domains, the domain of f and the domain of g simultaneously. So we put all these together with a conjunction. That's what I'm going to call the degeneracy system. Right? Now you might think, well, why didn't I need that location condition in the Lagrange system? Why don't I put the fact that x is in W? Okay, the reason is because it's obvious. It's just implied. In the Lagrange system, it's implied. The reason is because the vector x appears in the Lagrange system both plugged into G and plugged into the gradient of f. So to be plugged into G, it has to belong to the domain of G, which is V. To be plugged into f or its gradient, it has to be in the domain of f, which is U. So it's like implied by the equations themselves that such a value of x has to belong to both U and V. In other words, it has to belong to the intersection of U and V. Otherwise, it just wouldn't make sense to conjoin these two equations together. So there's no need to write that condition in that case. But you see that in the degeneracy system, the function f is not mentioned. The function f is nowhere mentioned. Only g appears here, and then here. So to keep f in the picture, to keep things relevant to the function f, we want to make sure that the points x that we consider are still in both domains. So you see f gets mentioned here, basically. U is nothing but the domain of f. And that's why we need that location condition for that degeneracy system. Okay, now this is an additional k scalar equations, as we saw before. They're of the form g1 of x equals c1 up to gk of x equals ck. So together we have k plus 1. This is a system of k plus 1 scalar valued equations in just d variables. And that's what we call the degeneracy system. Okay, let's talk a little bit about this stuff here, just to make sure we understand that this is a kind of grammatically correct expression. Okay, let's remind ourselves that the function g goes from an open set in D space into K space, and K is the lesser of those two. So the derivative matrix is, you have to read it, remember you always read it backwards like that. So the derivative g prime of x is going to be of size k by d, and its transpose therefore is d by k. So this product makes sense, and the size of the product is k by k. Notice that that's square, and therefore it has a determinant. The determinant is well defined. Right? But the fact that the determinant is set equal to 0 means that that square matrix is not invertible. That's really what the degeneracy condition is saying, is that that square matrix is not invertible. There's a word for not invertible. It's called singular. So a matrix is said to be singular if it's not invertible. A square matrix only applies to a square matrix. Okay, now in the interest of complete honesty, when I wrote this condition in a prior video, the first time you saw it, I wrote it backwards. I wrote g prime transpose times g prime. Now that's actually okay too. There's nothing wrong with that. It's just not the preferred way. Let me explain. So, we already said that g prime of x is k by d, and this one is d by k, it's transpose. So you see that the product still makes sense in this order, and it's going to be of size d by d, which is still a square matrix. So the determinant is still meaningful. And in fact, it turns out that this product here is singular precisely when this other product here is singular. So although those two matrices are not the same, those are not the same matrix. One of them is a k by k square matrix, the other is a d by d square matrix. So if k and d are different, they're not even of the same size. But even if k and d were equal, they still wouldn't be the same matrix necessarily. Anyway, it doesn't matter though, because even though they're not the same square matrix, it turns out, we're going to see this later, one of those two square matrices is invertible if and only if the other one is. So one of them is singular if and only if the other one is. And that means that this equation here is completely logically equivalent to this equation. So you can use one of those equations or you can use the other one completely indifferently. It doesn't affect the truth or falsehood of the degeneracy system at any point, because the two equations are completely logically equivalent. So the way I had written it first was not wrong. It's still correct. But why is this one preferred? Why is this one here preferred? Well, it's simply because since k is the smaller of the two in general, I mean, they could be equal. K and d could be equal. It's possible. But usually, in practice, in most cases, k is going to be less than d. And therefore, a k by k square matrix is going to be easier to compute the determinant of, because it's a smaller matrix. Okay, that's why this one is the preferred one. K by k is an easier determinant to do than a d by d, meaning to compute it. Okay, so anyway, that's the full statement of the theorem, and now we want to get into the details of the proof. All right, the proof relies heavily on the intermediate value, I'm sorry, not the intermediate, the implicit function theorem. The implicit function theorem, okay? So let me explain how this is going to work. What we're going to do is, we're going to have our function big F of x, which is just going to be our constraint function minus the constant c. And therefore, when I set this equal to 0, that's completely equivalent to our constraint equation, g of x equals c. So I'm just defining big F in this way. All right, now, if you remember the implicit function theorem, the idea was we have a function big F of some variables equals the 0 vector. And what we want to do is we want to subdivide those variables into two classes. We can call them like y's and z's. And then we have to get the numbers right. Basically, if you have 3 equations, you can only expect to solve for 3 of the variables. Excuse me. Okay, now we know exactly how many equations we have because we know that f is k-dimensional, the outputs, which means, by the way, that this 0 vector is also the k-dimensional 0 vector. All right, how do I know that? Well, we know that g of x is k-dimensional outputs, and then this c is also a point in k-space. So when you subtract the two, obviously you're still getting a point in k-space. And that means you have k equations here, right? It's like f1 of x equals 0, f2 of x equals 0, up to fk of x equals 0. System of k equations. So we can only expect to solve for k out of the d variables. And we can only expect to do it locally, near a solution point. Some special solution point, okay? Because that's what the implicit function theorem helps us do. So we're going to solve for k of those variables in terms of the other d minus k. Now notice what that means when d is equal to k. If it so happens, let's make a little note. If it so happens that k equals d, then we're solving for all d of the variables locally, near a point, particular point. So then there are no parameters left. That generally doesn't happen. In practice, the number of constraints is usually smaller, strictly smaller, than the number of variables. So you see, if k is strictly smaller than d, then we're going to solve for k variables in terms of, as functions of, the remaining d minus k, which will be positive. So in other words, our solution is going to be parametric. We're going to take those d minus k variables as parameters, and they will parameterize the solution set. But you see, in the case when k happens to equal d, then you have 0 parameters left, because you're actually solving for all of the variables locally. Okay, so then you'll just have sort of like a unique solution point in a neighborhood of... Well, you already have a solution point. You have a special solution point in a neighborhood of which you are solving. So anyway, we'll see how that plays out later on. Okay, but we still have to partition the variables into those two classes. One class is going to have, k variables. Let me do this in some color. Let's call those y's. And then you'll have those d minus k remaining variables, which we'll call the z's. And the goal is to solve this equation here locally near some special solution point to solve for these k as an implicit function of these d minus k. All right? But of course, you can't just go and do that for any selection of k out of the d variables. You have to have a certain non-degeneracy condition. So we have to talk about how that's going to work. But that's just a small reminder of how the implicit function theorem works. By the way, the special solution point that I keep alluding to is simply the point P. Because the point P is the point that we wish to prove things about. We want to prove that it satisfies either the Lagrange system or the degeneracy system. So it's the point P that's like the special focus of our investigations. And it is a special solution point because G of P is indeed equal to C. How do I know that? Well, I know it because the point P is assumed to belong to the set S. And the set S is the constraint set. This is true by hypothesis. Since S is the constraint set, every point in S must satisfy the constraint equation. So P in particular must satisfy that constraint equation. So when you plug in x equals P, you get a true equation on that side, and therefore you also get a true equation here. In other words, it is true that f of P equals 0. So P is a solution point. And that's the point in whose neighborhood, in whose vicinity we will be working. Let's make sure we recall that P really is in the set S. Right? Remember, we assume that right here. There exists a point P that's in S. So the fact that P is in S is certainly something that we have to work with as a hypothesis. Okay, now remember that the implicit function theorem has its own hypotheses. In order to be able to apply it, there's a non-degeneracy condition involved. And the idea is that if we have this, where we have two groups of variables, and let's say that y is k-dimensional and z is d minus k-dimensional, and of course f has outputs in k-space. So notice it's very important that these match, because we're going to have k equations to be solved for, we want to solve locally for exactly k variables, namely the y variables, in terms of, in other words, as implicit functions of the z variables, of which there are d minus k. All right? And, in the case where d is equal to k, then this will just be the empty set of variables. Our solutions will just be numbers rather than functions. They won't be functions of z1, z2. They'll just be explicit numbers. Okay. Anyway, so what was the appropriate non-degeneracy condition? Okay, at the special solution point. Now, actually, first I should say, the special solution point has to be broken down. It's P, but we have to break it down into two groups of coordinates. The first k coordinates, let's call A, and then the last d minus k coordinates, let's call B. So when you concatenate those, you still get, d coordinates in total. So another way to say this is that A1 is P1, A2 is P2, AK is PK, but then B1 is PK plus 1, B2 is PK plus 2, and finally BD minus K is PD. So we split up the coordinates of P into these two groups, and we call one group A and the other group B. All right, now, what was the non-degeneracy condition? For the implicit function theorem to be applicable? It's that when you take the partial derivative of that big F with respect to just the y variables, just the variables you wish to solve for. Remember, it's the y variables we wish to solve for as functions of the z variables. And you plug in that special solution point, then this should be an invertible matrix, meaning that its determinant is not equal to 0. Okay, so another way to say that is just that this matrix inside is invertible. We should check that it's really a square matrix. Okay, it is a square matrix, and I'll just show you quickly why that's true by reminding you what these partial Jacobean derivatives are all about. Okay, the partial Jacobean derivative goes like this. You're going to take the first component function, f1, and partially differentiate with respect to the first of the y variables. In fact, I should probably give myself a bit more room here. Then you do the same with the second component function, all the way up to the last component function, which is the kth one, all with respect to y1. Oops. Okay, then the next column is going to have the same stuff, but with respect to y2. Oops. Can't quite write that there, but you get the idea. But that's just like a dead spot on my screen where I can't really write. And then it goes up to yk. So you see that this is a k by k matrix. It just so happens to be. Why did that happen? Well, simply because these two dimensions matched. That's the importance of that. Makes this a square matrix. Now that's not the full Jacobean derivative. Remember, the full Jacobean derivative, f prime, which you can also write as like df dy z, or just df dx. Okay, that would involve same idea, right? But you're using all the variables. So like in this column, you'll have all the component functions with respect to x1. In the last column, you'll have all the component functions with respect to xd, which is the last of the x's. So this is a matrix of size k by d, as we remember. Reason? F maps a domain of d space into k space. That's because it's really just the function g, but minus a constant. So it has the same domain as g, and also the same codomain. So the derivative matrix is like k by d. You have to read it that way, k by d. But you see, in terms of the y's and the z's, you can also write it this way. You'll have f1 with respect to the first of the variables, which happens to be y1. Then eventually you're going to have all the component functions with respect to yk. And then the very next entry in that row is going to have like z1. All the component functions with respect to z1. And that's going to keep going until you reach d minus k. Oops. So you see that what we're really doing is we're partitioning up the ordinary derivative matrix, which is k by d, into a k by k block, and then another block of size k by d minus k. And those are partial Jacobians, which we write like this. We can write this first block as df dy, but notice that it's still a function of all the variables, x. In other words, it's still a function of the y variables together with the z variables, because each individual partial derivative depends on all of those variables. Okay, and then the other block in there would be the partial Jacobian with respect to z. But again, it depends on all the variables. So we have this general breakdown into these partial Jacobians. Okay. Anyway, this k by k block should be invertible, and that's when you can solve for the y's implicitly as a function of the z's, at least in the neighborhood of the special solution point. Right? There's going to be some neighborhood of the special solution point in which we can solve the original equation, big F equals 0. Solve it for y as an implicit function of z. Okay, and remember that the implicit function. So okay, I'll remind you that there's implicit function theorem says that there exists neighborhoods. By neighborhood, I mean an open set containing a given point. So if I talk about a neighborhood of A, I mean an open set that contains A in it. Okay? So there are open neighborhoods. Let's call them NA. Should I call them that? Maybe I'll simplify the notation a little bit and just write like capital A for a neighborhood of little a. Should I? No, let me use the other notation. Okay, I'll just write it like this. So n sub A is a neighborhood of the point A. It's going to be some open set in K space. Then there'll also be a neighborhood n sub B, which contains the point B, and is an open set in D minus K space. And there's going to exist a function, psi, which is the implicit function, which is going to map one of those neighborhoods into the other in a C1 fashion. Remember, the fact that the implicit function is C1 is all part of the conclusion of the implicit function theorem. So this psi is the implicit function, okay, such that subject to the locality conditions, meaning that the variable y has to be restricted to this neighborhood of A, so that y is quite close to A, and the variable z has to be restricted to this neighborhood of B, so that z is quite close to B. Because remember that the implicit function theorem is only a local theorem. It requires everything to be close to the special solution point. Right? But subject to those locality conditions, we have the equivalence, what we call local equivalence. That the original equation, big F equals 0, is equivalent to y equals psi of z. Okay, so y has been solved for as an implicit function of z. Right? But it's only subject to, meaning these conditions have to hold before we can conclude that this biconditional is true. So from a logical point of view, what this is really saying is that, like, for every y in this neighborhood, and for every z in this neighborhood, the equation big F of yz equals 0 holds if and only if y is equal to psi of z. Okay. Anyway, so question for us is, if we plan to use the implicit function theorem, we need to check that the non-degeneracy condition holds. Otherwise, you can't apply it. So how do I know that? Okay, so let's take a step back and just talk about a general point of logic. Okay, I claim that if we have a disjunction, let's say I have some disjunction. So first of all, everybody knows that that's logically equivalent to this disjunction. Like, disjunctions are commutative. But I also claim that this can also be written this way. Not A, then B. I can write it as a conditional, in other words. If not A, then B. And by the same trick, on this side, I can also write it as if not B, then A. Actually, the equivalence of these two is clear from contraposition, contrapositive. Because everybody knows that if you take a conditional, if A then B, that's logically equivalent to its own contrapositive, which is where you reverse the order of the antecedent and consequent clauses, but also negate both of them. And if you just do that to this conditional here, right, you'll get not B, then not A. But the double negation can be cancelled, so then you get that. So it's clear that those are equivalent just by contraposition. All right, what's the relevance for us? The relevance for us is that we have a disjunction that we want to prove as our conclusion, our desired conclusion. That we wish to prove is that the point P satisfies either the Lagrange system or the degeneracy system. So in other words, we have a disjunction that we wish to prove. We can take A to mean that P satisfies the Lagrange system, take that to be the meaning of A, and then take the meaning of B to be that P satisfies the degeneracy system. So how do I prove that disjunction? Remember, P is not just any random point, but it's assumed to be a global maximum of the function f restricted to S. In this context, P is assumed, I'm just recalling for you, to be a global max point of f restricted to S. So it's not just an arbitrary point P that I'm talking about here. But anyway, how do I prove a disjunction? Either P satisfies this system or P satisfies that system. Well, we can prove the disjunction by just rephrasing the disjunction in this form as a conditional, because conditionals are very easy to prove. Let me talk about how we prove a conditional. To prove a conditional, let's say if P then Q, what you do is you start a new subproof or subderivation, which is isolated from the main proof, in the sense that within that subderivation, you're allowed to make new assumptions, as long as you use those assumptions for a correct logical purpose. See, in general, you can't just make new assumptions. You're given what you're given, and you have to prove what you have to prove. You're given some givens. You can't enlarge the set of givens. And you have to find a way to reach the desired conclusion just from what you're given. Okay? But in a subderivation, you can make new assumptions. Give yourself more to work with, as long as you use those new assumptions properly. Okay? And so what you do is you start a new subderivation based on the assumption, based on the, let me call it, additional assumption. Additional meaning beyond what you were given. That the antecedent clause, P, is indeed true. And what you do then is you just show that the consequent clause, Q, can be derived from P, meaning your new assumption, together with everything else you were given previously. Oops. Okay, so it looks like this. I'll sketch it out for you. You have your main line of argumentation, or reasoning, and then what you do is you, so like at the top, okay, schematically speaking, you have your givens here. You have your, everything that you were given. These are called your hypotheses. The hypotheses of the theorem to be proven. Okay, down here you're going to have your conclusion. And you want to reach that step by step, moving in the downward direction. In other words, every new line you write has to be justified by appealing to some preceding lines. Then you'll write another line and you have to appeal to some preceding lines. Okay. But somewhere within that proof, so I'm showing you here is like a schematic structure of a proof in general. Somewhere within that, you can create a new subderivation, schematically drawn by its own little line within a line. This thing is called a scope line or scope marker. What it shows is all the steps in the proof where these assumptions here are in effect. Everywhere within this scope line, within this main scope line, those assumptions are in effect. Those are being assumed. Okay? But within this other scope line, or scope marker, which is nested inside, we can have a new assumption. And this is just an assumption we're making for the sake of argument. Meaning we don't make it just randomly. We make it for the sake of logic. You have to do it in a very prescribed way. You can't just do it randomly. There are certain rules of logic that tell you, when you're allowed to make a new assumption. Okay, something you're used to that looks like this is proof by contradiction. In a proof by contradiction, the assumption you would make is that the conclusion is not true. For instance, if you assume that and then you eventually derive a contradiction, then what you would do is you would close your subproof. Close your subproof. Subproof ends right there, and what you conclude is that the conclusion must be true. Okay, so you see the assumption you're making is always limited by some rule of logic, such as proof by contradiction. Okay, that's just one example of a subderivation. But you see that the assumption that the conclusion was false, this assumption here that you made, that the conclusion was false, only takes effect inside this scope marker. Once you close that scope marker and you go down here, that assumption is no longer in effect. That was just a side tangent. You made that assumption only as an aside in order to explore the consequences of making that assumption. Once you had fully explored those consequences, namely seeing that they're contradictory, you then reject that assumption. That's when you close that scope marker. Okay. Now in our case, what we're going to be doing is, to prove a conditional, we would open up a new scope marker inside, and we would assume, as an extra assumption, the antecedent clause. And then, using the givens as well, because those are all still in effect, whatever givens we had here are all still in effect, but also using P, which is now also in effect in here. Using all those together, the idea is to try to derive the statement Q. And, you do it step by step. Like every line you write down has to be justified by some preceding lines. You write down the next line that has to be justified by some preceding lines. But eventually, suppose you reach Q. Well, then you can close your subderivation. And what you conclude in the main scope line is the conditional, if P then Q. And what you appeal to, so-called conditional proof. That's the technique. Just like there's proof by contradiction, which would be the justification for this step here. Once you close your internal scope marker, you would say, okay, the justification is proof by contradiction. Or indirect proof. Well, it's the same here. This is just technique is called conditional proof. You prove a conditional by showing that the consequent clause, Q, can be derived with the assistance of the assumption P, which is the antecedent clause. Okay, that's the technique. So coming back to our case, remember that the statement A for us signifies that P satisfies the Lagrange system. That's what this is. Okay, and then the statement B for us signifies that P satisfies the degeneracy system. So what about the negation of B then, which is what here appears here? Well, that signifies the statement that P fails. Oops. Which was that little dead spot. Sorry, let me make a bit more room here. Okay, the negation of B would signify for us that P fails the degeneracy system, fails to satisfy it. And what we need to prove then is the conditional, this conditional right here. Right, this conditional right here. So we need to show that if P fails to satisfy the degeneracy system, then P does satisfy the Lagrange system. That is the same conclusion. That conditional statement is exactly the same conclusion as the original conclusion, which was this one. Those are logically equivalent to each other. But once we phrase it as a conditional, we can use the technique of conditional proof, which would be to assume that P fails to satisfy the degeneracy system, make that an extra assumption, and based on that extra assumption, plus the given hypotheses, we would wish to derive this. Wish to derive that P must be a solution of the Lagrange system. Okay, so that's the logic here. The logic for us is going to be that we're now going to make the additional assumption for the sake of conditional proof, the technique of conditional proof, that P is not a solution of the degeneracy system. And then our task, our goal, is to show that P must be a solution of the Lagrange system. And with that, we'll complete the proof. So we now have an additional assumption on our hands, namely that P is not a solution of the degeneracy system. So let's see what that really means. Our extra assumption, what it really means is that the determinant of G prime of P times G prime of P transpose is not 0. Okay. Now you might balk at that, because if we go back and we look at the degeneracy system, we remember that it really is a pair of equations. Actually, no, it's 3 conditions. So if P fails to satisfy that conjunction, like let's say I say that P fails to satisfy this conjunction. Well, there are a number of ways that can happen. Maybe it fails to satisfy this, but maybe it fails to satisfy this. Maybe the reason it fails the conjunction of the 3 is because the second condition is false. Okay, but that's not true. We can see that that's impossible, because we do know that G of P is equal to C. G of P is definitely equal to C. So the constraint equation is not the one that fails. What about the location condition? Could that be the one that fails? Answer is no, because we do know that P is in W. Why? We know that P is in S, actually, and S is already a subset of W. So therefore P is certainly in W. So it can't be that one that fails. So if P fails to satisfy the degeneracy system, it must be because that equation is false. And that equation says that the determinant is equal to 0. So if that equation is false, it just means that determinant is different from 0. So we're correct in concluding that our extra assumption looks like this. This is completely equivalent to saying that the point P fails to satisfy the degeneracy system, because that's the only way that P could possibly fail to satisfy the degeneracy system. The other 2 conditions must be satisfied by the point P. We know that already. It's only that condition that could possibly fail. So that's our extra assumption we're going to work with from now on. We can work with this from now on. And that's a good thing, because that is exactly what we need in order to have the non-degeneracy condition from the implicit function theorem come out true. Okay. Now, what's the link between the 2? All right, well, one link is just take notice of the fact that because big F is essentially the same function as g of x, they just differ by a constant, it follows that big F prime of x is the same as g prime of x, and specifically at the point P. Big F prime of P is the same as g prime of P, which is exactly the matrix that appears here. So we can just rewrite that if we like as big F prime. And that's because, everyone knows adding or subtracting a constant makes no difference when you differentiate. That will differentiate to 0. So that's why this condition is true here. All right, so our extra assumption, therefore, that we can now work with can be written in this form. The determinant of big F prime of P times big F prime of P transpose is not 0. All right, but what's the connection to like those partial Jacobians and all that, right? So I have to do a little bit of a detour to make that connection. All right, so let's just do a little bit of an aside, a little detour in linear algebra. Talk about the Gramian of a given matrix, just briefly. Here's the idea. I have a matrix. Let's say its size is like, well, actually, I'm going to be careful to keep the notations the same. Oh, what did I just do? Okay, yeah, let me keep the notations the same. So the matrix A that I have in mind to apply all this stuff to is this matrix here. And so what's the size of that? Well, it goes from, the mapping F goes from D space to K space. And so we have to read that backwards. So it's K by D. And let me just keep that notation here, K by D. All right, so anyway, A transpose is then of size D by K. And the product of those two is of size, oh, in this order, like transpose times, the A transpose times A in that order is D by D. So it's a square matrix. And that matrix is called the Gramian. This is named after Gram, of Gram-Schmidt fame. Okay, so we can have a notation, I'll call it like just little g of A. But I'm not really going to use that notation very much. I'll just write out the product, A transpose A. But if we like, we can call it g of A. Notice that it's a square matrix. And the theorem is that the original matrix A... Oh, so, okay, sorry, before I state this, let's just go back and remind ourselves here that we're assuming K is less than or equal to D. And the reason that's relevant is because I'm going to talk about the rank of A. And we remember that an upper bound for that is the smaller of the two dimensions. But I don't really have to write this, min of KD, because we know what that is. We know that that's just K, since K is the smaller of the two. So K is the upper bound for the rank. And that means that having full rank means having rank exactly K. So A has full rank if and only if the rank of A is precisely K. All right. So the theorem is that A has full rank. That is, the rank is exactly K, if and only if the Gramian matrix is invertible. Another way to say that is if and only if the determinant of the Gramian is non-zero. Okay. And if we put that differently, using the contrapositive, putting this in a contrapositive form, the determinant of the Gramian is equal to 0 if and only if the rank of A is less than K. It's not full. Okay. So we're going to prove this in a moment. Oh, and by the way, we can add second theorem that if I look at the Gramian of A transpose, now remember, when you form the Gramian, you have to take the transpose of your given matrix first, and then write your given matrix after that. So that would be just A times A transpose. That's of size K by K. Right, the original matrix A was like K by D. The transpose is D by K. All right, and notice that the original Gramian was not K by K. The original Gramian was D by D. So the Gramian of A is not the same thing as the Gramian of A transpose. But it turns out that those two Gramians, G of A transpose and G of A, are either both invertible or both singular. They're invertible together, or they're singular together. That's another interesting theorem that we can prove easily. Okay, but all right, before getting to the proofs of these theorems, let's just see why are they relevant to us. Okay, well, we have this extra assumption now, right here. So we know that the determinant of this Gramian is non-zero. And from the theorems we just stated, what that tells us is that that happens if and only if this matrix F prime of P, which is my matrix A, is not of full rank. I'm sorry, it is a full rank. Namely, of rank K. Because remember, the non-vanishing of the determinant, the fact that it's not equal to 0, means invertibility. Means that the square matrix inside is invertible. Okay. Yep, and then the invertibility of that Gramian is equivalent to the fullness of rank of the original A. So our extra assumption can now be put in this form. It's the fact that f prime of p is a matrix of full rank. We're going to use it in that form. Okay. Let me stop the video here, and we'll, just to avoid it becoming too long and having trouble uploading, and then I'll complete the proof in the next video.